Before we get into mag particle, let's talk about indication types and method selection. This is a short one, but just so you understand that, and still got the bench on there. So when we're doing NDT, there are three indication types or three flaw categories that we may see. And so when you perform some kind of a test or inspection, the thing we're looking for, what we want to find, are real or relevant indications. And those are a true flaw. That can be something like a crack, corrosion, thinning, a disc bond if we're doing composites, something like a disc bond or delamination, and that kind of thing. So those are known as real or relevant. And when you're doing your labs, you're going to have to classify the indications that you get as relevant, non-relevant, or false, which are the other two. So non-relevant is there's going to be certain indications you get due to features of the part. Okay. When we do, we'll look at something like liquid penetrant where we put a dye on a part. An object with a rough surface it's harder to clean off a rough surface than it is a smooth surface. And so a certain amount of that dye is going to stick behind and you're going to get an indication. There's going to be dye that stays there, or even the magnetic particles, you're going to have more particles sticking to a rough surface than you will a smooth surface. And so you'll get an indication because of that. It could also be something like a forging mark or other tooling marks from the production process. It can be things like because of things like paint or other surface treatment. And those kind of things. So that's a non-relevant. It's an indication we expect to get because of some feature of the part. It could be the geometry where a part, if there's if there's like a 90-degree corner, fluid or particles can get kind of trapped in the corner, right? It's hard to clean out sharp corners inside of you think of like you're washing like a glass, right? It's hard to get that bottom edge the cleanest. So non-relevant falls in that category. It's not an indication of a failure, of an impending failure. It's a feature or an unintended indication because of the geometry or surface finish. A false indication is something caused by a process error. This is a mistake. And so when we get into things like liquid penetrant, we have to wash the parts. It could be insufficient or overwash. Things like what are called dwell time. It can even be things like thumbprints, fingerprints when you're handling a part that has the different NDT consumable type materials on it. It can be when we're doing things later on like ultrasound or eddy current, when you're moving a probe over the surface of the part, if it wobbles a little bit, or if you break contact for a second and you get an indication on the screen, that would be a false indication due to an error. And you're learning the techniques, you're going to make errors, so it's likely that in your reports you will be able to discuss the false indications that you get. Even a very experienced NDT technician will get false indications, right? They may be moving a probe around and it wobbles a little bit. The reason that's important is you need to be able to recognize that and be able to say, this was because I wobbled the probe, this is because I went across a crack. This is because I wobbled the probe, this is because I went over a rough surface, and this is because I went over a crack, right? So that's why being able to determine the three indications is important. Okay, so relevant, a true flaw, non-relevant, geometry of the part or surface finish, false is caused by a mistake. And for every indication that you discuss in your lab reports, you're going to have to classify it as one of these three. Metallurgy, the other thing we need to look at is when we're choosing NDT methods, or various NDT methods have been developed to work with different materials. So one of the big keys, if we're looking at metals, is whether they're ferrous or non-ferrous. Okay? What does ferrous mean? Where does the term ferrous come from? What do the ferrous metals contain that the non-ferrous metals do not? Iron. Okay? Iron, the chemical symbol Fe, ferrite. Okay, that's where they get the name ferrous. So iron-containing metals typically can be magnetized, and that's important because several of these techniques we're going to use rely on magnetism. Okay? When you have most parts are not made out of just iron. They're made out of some kind of an alloy, a steel, and steel then can contain things like carbon, silicone, tin, copper, nickel, and that at different percentages. And at the end of the day, that's not, for what we're doing, you would need to understand that if you're designing tests and that kind of thing, but you can't go up to a piece of metal and say, okay, this is steel and it's this specific alloy without, a lot of kind of lab testing and that kind of, unless it's marked, right? When you're working with the aluminum, which is non-ferrous now, in the lab, right, we have it stamped on there, 2024 T6 or something like that. But if we just had a bunch of pieces of aluminum sitting there with no indication, you wouldn't be able to tell, 2024 T6 from 2024 T7 or, 6068 from 2024, right? They all look the same to the naked eye. It's most of the time. So that's your ferrous. Non-ferrous typically cannot be magnetized. So things like titanium, aluminum, brass, which is a combination of copper and zinc, or bronze, copper and tin. And then stainless steel kind of falls in the middle. Most stainless steels are non-magnetic. The reason they're non-magnetic is because they contain the chromium. That kind of screws up that. But for testing, we can oftentimes use methods that rely on magnetism. Because anything, in theory, anything can be magnetized if you run a strong enough magnetic field or current through it. It's just that if you try to magnetize plastic, it's going to melt or burn before it ever gets magnetized from the amount of energy you have to run through it. Okay. But some of these will develop a temporary magnetic field during the inspection process, like when we do eddy current testing. That induces a magnetic field in any of these, but that magnetic field only is there while the probe is on the part. As soon as you pull it away, that magnetic field collapses. It doesn't maintain. You can't magnetize it permanently or even temporarily. Now with any of these, all metals in some way or another are electrically conductive. And so for certain techniques that we perform, we have to have the ability to conduct electricity. Okay? So there are techniques that rely on electrical conduction as well as magnetism or lack of magnetism, and it affects how the techniques work. The other thing to keep in mind is how parts are made and fabricated. Okay, now we also have non-metal parts, right? And we'll get to that in a minute. But you've dealt with composites, fiberglasses, glass fiber reinforced plastic, GFRP is the official name of it. Carbon fiber reinforced plastic, CFRP, carbon fiber, right? Glass, resins, plastics, all that stuff, right? Those have their own techniques that they wouldn't be able to use the techniques that rely on magnetism or conduction. They have to have techniques that don't use that. But with all these metal parts, we have things like casting, forging, extrusion, rolling, and machining. And those kind of go back to those different flaw indications. A part that is a rough forging or a rough casting is going to have a rough surface. And so it's going to cause non-relevant indications because of that. Rolled parts tend to have a little bit smoother surfaces, or polished or machined parts can sometimes be mirror smooth. And that's going to have it's going to interact differently with the different testing materials and testing chemicals than something with a rough surface. So you got to take that into mind, keep that in mind when you're doing different techniques and trying to decide what's appropriate and what kind of indications are you seeing. So when we're deciding on methods, we have to take into account things like technical capabilities. What equipment do you have? What are you trained to perform? There might be more than one technique you can use to find a flaw. Right? You might be able to find a flaw using an eddy current tester or dye penetrant, a crack, for instance. But I can tell you, liquid penetrant and spray cans is a lot cheaper. I think spray cans, they're about $20 to $50 a can, which sounds like a lot, right? But you need 3 cans, okay? So you're talking $100 for the equipment to do dye penetrant inspection. An eddy current tester starts somewhere in the $10,000 to $20,000 range. It can find even smaller flaws, but if you know the other part of it's training. It's a lot more people are trained and competent at liquid penetrant than doing eddy current. You'll see the difference when we do both of them. So, technical capabilities. What do you have the equipment for? What kind of expected flaws? Are you looking for cracks, corrosion, Delamination, disc bonds, is it a surface flaw? Is it a subsurface flaw? Different methods and techniques will work for different things. Criticality, how critical is it that you find it? You can have a little bit of micro cracking. It's not going to hurt anything. You can use a less sensitive, less expensive, easier to do method. The fan blades I talked about last time, super critical you find it. You have to use that eddy current test to find it because you got to find the cracks before they're big enough to find them using liquid penetrant. So there's, criticality plays a role in it. Cost, I talked about that. Cost of equipment, cost of consumables, time, training kind of goes into cost, right? It costs money to get trained. It costs your time to get trained. Type and size of part. Some equipment requires, X-ray. A small X-ray cabinet, you're talking $100,000. You want to X-ray an entire airplane spar, you're going to have to get portable equipment, right? So do you have the right equipment to do it? Using a bench versus portable equipment. Using small probes versus larger probes. Using a single probe where you got to go around areas like this, or having an array where it's a big sheet you can slide across the surface and do a lot all at once. Okay? Again, that goes back to cost as well. Right? You can do the same thing when we do eddy current. You've got a little pencil probe. You can check for cracks around every rivet by doing that. Or you can get a big sheet of an array, a whole bunch of probes all together where you can run that over and do a big area much quicker. But that array probe and the tester that goes with it costs a lot more than the pencil probe and the single channel tester that you would use. So you got to decide what's that. Environmental conditions. Some things can be done in bad weather or outdoors, other things can't. Some things are temperature sensitive, time sensitive, others are not. If you're trying to do thermography, which is infrared imaging, you can't do it on a bright sunny day because all you'll get is the heat of the sun reflecting off of all your surfaces. It'll wash out any ability to see what's going on in the part. And then type of material, like I was talking about. Is it metal? Is it a brass? Aluminum? Different reinforced plastics? Whether it's fiberglass, carbon fiber, or aramid fiber, or other stuff. Aramid fiber is Kevlar, by the way. So you got to take all that into account. Okay? So that's kind of the last intro, and that was what I wanted to do before I opened up quiz 1.